Hello everyone, my name is Josh and welcome to today's video on differentiation. Now, I'm going to go through differentiation at a GCSE level, not A level, that's important to note. So it's going to be differentiation for use of finding turning points of graphs and rates of change, things like that, not advanced level differentiation that you would need for A level. So if that's what you're looking for, then this video isn't the right one for you. So I'll start with a small introduction to differentiation. So differentiation has two different possible notations. You can have dy by dx notation, or you can have f prime notation. So these two statements mean the exact same thing. It's basically the same as what I was talking about previously, a rate of change of a graph. So like y2 minus y1 over x2 minus x1. So just in the same way, it finds the gradient of a graph. This is just a different notation you can use for it. And in doing so, you can use different ways to find the gradient. So the notation you would use is really up to you, but if you're given an equation like fx equals 3x squared or something, you'll want to use f prime notation for its derivative. And if you're given y equals x cubed plus 3x or something like that, then you'll want to use dy by dx. Just match up the notation with the equation that you're given. So in terms of differentiation, there's rules that you can use. So the syllabus that I'm looking at tells me that you only need to know integer powers of x to differentiate. So the general rule of thumb is if you've got an equation, it's y equals x to the n, then when you differentiate it, you get dy by dx equals nx to the n minus 1. So all you do, you take the power on x, times it by x, and then subtract 1 from it. So, for example, if you had an equation that was equal to y is x to the power 5, then the derivative of that equation would be 5x to the 4, because we've just taken this, dropped it down here, and taken 1 off of it. And that's all there is to integer differentiation. If you've got multiple terms like in this one up here, you just do each one at a time. So dy by dx equals 3x squared plus 3, because here you've got x to the 1, that's x to the power 1 like that. So times by 1 gives you 3x still, and then you get that turning to x to the 0, which equals 1. So you just end up with 3 there. So if you have only one x, like x to the power 1, it'll just drop out and give you its coefficient. So that's all there is to do for integer differentiation. You just need to go through each term that's being added or subtracted and multiply it and then subtract 1. So I'll do one example of a negative integer power, so y equals x to the minus 3, which is equal to 1 over x cubed. So if you're given something like that, you want to rearrange it so it's an n, like an x to the n format, to make it easier to differentiate. So you take that and take it to x to the minus 3, and then you would differentiate it to get minus 3x to the minus 4. Just doing the same thing again. Take this whole minus 3, times it by the x, and take 1 away, and you get minus 3x to the minus 4. You can also write that as minus 3 over x to the 4 if you prefer. whatever suits, or whatever format you're told to give the answer in. So differentiation is a very powerful tool. It can do lots of different things for you. Like I have to differentiate things all the time on my course in physics, but it won't have as much use in general life unless you're studying something maths related. So, but in terms of maths, it's quite a powerful tool. So, for example, I told you already that our dy by dx can get you a gradient the same way that I talked about in our equations of straight line graphs video. So, for example, if you're told to find the gradient of a tangent of an equation, so let's say it's here, y equals x squared plus 3, and we're told to get the gradient of a tangent at a point 1, 4. So we just want to get the gradient at this point 1, 4. Well, one way we can do that using this notation, so you generally use this if your graph isn't drawn to scale, because if your graph is drawn to scale, you can just do the same thing as the straight line graphs question, as the straight line graphs style that I went through in the previous video. But if not, then what you would do here, you would take dy by dx is equal to 2x, because this 2 goes in front, and then subtract 1, that's x to the 1, so 2x. And 3 doesn't have a power of x. So when you differentiate something that has no power of x in it, it just disappears completely. It just drops out of your equation altogether, so you just end up with 2x. So that's the equation, that's the gradient that we've got. That's equal to m, the gradient of our tangent. So then we want to find the equation of this tangent. Well, we just do this the exact same way. So we've got this coordinate here that the tangent passes through. So we have 4 equals 2 times 1 plus c. So from here we've got 4 equals 2 plus c. And then rearranging for c equals 2. So then that gives us an overall equation of this line as y equals 2x plus 2. So that is the equation of the gradient of this line. So we can just check that the tangent is right if I plot this graphically and show you now. So here is the graph of this solution drawn properly, and you can see just by looking at this that there is a tangent at the point that we calculated. So we know that this method has worked, and this is the case for like any time you take the derivative of a function, whatever the function is, and you sub a point in like this, you will get the gradient at that point. So the gradient of the tangent to that point. So another use of taking derivatives is you can use it to find the turning points of graphs. So this means you can use it to find the coordinates that a graph turns at. So if we had this graph, for example, finding the turning point would mean finding this point at the very bottom of the well. Now, the reason we're able to do this is because one very special fact about this point is that it has a gradient of 0. So whenever you find part of a graph that it turns, so say we have this cubic graph or something, this would be a stationary point or a turning point, and this would be a stationary point or a turning point. It's the same thing, it's just different ways of calling them. Because at any point that the graph turns like that, its change in y over its change in x should be 0. because it's not increasing or decreasing at that point. It is just completely still. That's why it's called stationary, because it's not going anywhere in either direction. So you may be asked at GCSE level to find the stationary point of a graph. So the equation that we're going to try and solve, I'm going to make one up. I'm going to say y equals x cubed minus 3x, that is supposed to say x squared minus 4x plus 3. So we want to find from this equation the stationary points, which are the same thing as the turning points. Now, at a stationary point, as I've mentioned, dy by dx is equal to 0. So, what this means we need to do is take a derivative. So we'll take the derivative dy by dx is equal to 3x squared minus 6x minus 4. Sorry, losing my voice. So all we've done here is go through and do the same method again, taking the 3 down, subtracted 1, taking the 2 down, subtracted 1, and taking the x out and taking the 3 out. 3 just drops off. So we've got this derivative here. Now, at stationary points, dy by dx is equal to 0. So that means that 3x squared minus 6x minus 4 is equal to 0. So this is looking like something we know what to do with. So because we're trying to find the coordinates, which means we need to solve this quadratic equation to get values of x and y of the turning points. So to solve this equation, I'm just going to substitute it into the quadratic formula. So x equals 6 plus or minus the square root of 36 minus 4 times 3 times minus 4 all over 2 times 3. If you don't know what I'm doing here with the quadratic formula, just check out my first video, which was on solving quadratic equations, where I explain this process. So this is equal to 6 plus or minus square root of 84 over 6. So this gives us solutions of x to be 2.53 or minus 0.53. So that's just quickly working out what they should be so it's easier to see on a graph. But you'll want to put an exact solution in when you're working out y, otherwise you'll get errors. So the next part of solving this is, so all of a sudden some information has just moved across the screen, pay no attention to it. So the next part of solving this question is we want to solve our y values. So we've got our x values for the turning points, and we want to find some y values to match them. So that means we need to sub in our x values. So sub in to equation 1, I'm going to call it. Sub into 1. So we want to sub into equation 1 our values of x, which are given here. So subbing them in, all we do is just replace every x here with 6 plus root 84 over 6 and 6 minus root 84 over 6 separately to get our two values of y. So substituting those in, we find, so it'll be way too long-winded for me to write out all of that properly, but yes, so these x values just need to go all into this equation. So subbing into there, we find that y is equal to minus 10.1. So substituting in the negative value, that gives us minus 0.53. The y value for this coordinate is 4.12. So our overall coordinates are given by 2.53 minus 10.1, and the other one is given as minus 0.53, comma 4.12. So those are the turning points of this graph. And that's how you find the turning points or stationary points, or however you want to call them, for any graph. You just take a derivative, find where that's equal to 0, and at those coordinates is your stationary. So this is the graph of y equals x cubed minus 3x squared minus 4x plus 3. And we can see that the values we've got look to be about right. So that's about minus a half, and at that point y is equal to about 4. So that is consistent with this one that we worked out. And at this point, x is equal to about 2.5 and y is equal to about minus 10, which is consistent with this point. So we know that our solution has worked. And that the only way to check this is to check it graphically. So if you have the graph or can plot the graph, you can check that your solutions look right. So that's how to find stationary points. So the final thing I'm going to take you through in this video today is about whether your stationary points are maxima or minima. So what this basically means is a maxima looks like this, as in the stationary point is the maximum of a function before it starts decreasing, so that's a max. A minima is exactly the opposite. It's the minimum before it starts rising again. And there's one third type that it can be, which is a saddle point. So a saddle point looks kind of like this, where this bit in the middle has 0 gradient. So this one is called a saddle point. Now, the way we can tell which kind this is for any given graph is by taking a second derivative. So taking a second derivative, you write it like this: d squared y by dx squared. Or if you're using function notation, you can use it as f2 dashes x. So all this means is you take dy by dx of your function, so of whatever it is, like x cubed plus 3x squared, and then you take dy by dx again, like that. So that means you do dy by dx of, well, doing it on this gives us 3x squared plus 6x, and then we do dy by dx again to get 6x plus 6. Now, the usefulness of this is when we take the second derivative, if we find d squared y by dx squared is less than 0, it means that we have a local maximum. So yeah, if we have it less than 0, it's a maximum. If we find that d squared y by dx squared is greater than 0, it's a minimum. And if we find d squared y by dx squared is equal to 0, that means it's a saddle point. So you might be asked in an exam to classify whether your stationary point is a maximum, a minimum, or a saddle point. So all you do is take this derivative again, and then you want to sub in the coordinates of your stationary point. So I'm going to do this for our previous example. So we had y equals x cubed minus 3x squared minus 4x plus 3. So we performed dy by dx on this once, so we got dy by dx equals to 3x squared minus 6x minus 4, like that. And then we perform dy by dx again, so d squared y by dx squared equals 6x minus 6, just like that. So that is our second derivative. So what we want to do now is sub in the coordinates of our stationary points. So we only want to sub in the x values. We need to sub in x equals 2.53 and x equals minus 0.53. So substituting those into this equation, what we get is, so substituting in 2.53, we find that d squared y by dx squared is equal to 9.18. And 9.18 is greater than 0, which means that our one at x equals 2.53 is a local minimum. So we'll try it out with our other value of x. So we have minus 0.53 times 6 minus 6. And that gets us a value of d squared y by dx squared equals minus 9.18, and that is less than 0. And so that means that x equals minus 0.53. We have a local maximum. And that's all there is to do for these kind of questions. If you find you have a saddle point, so it's equal to 0, the question might want you to further prove what kind of saddle point it is by calculating some values around the stationary point, like say minus 3 to plus 3 of the stationary point, and show what's happening to y. So if y goes negative to positive afterwards, then it's a rising saddle point, and if it starts off positive and then goes to negative around it, then it's a negative saddle point. So that's all there is to do to find maximum and minima if they ask for second derivative tests. So that wraps up everything I'm going to talk about in today's video. Thank you for watching this. I hope that you found it helpful. If there's anything that you're unsure about or want me to explain a little further, just let me know either in the comments or over social media. If there's any more topics you'd like me to cover in a video, again, let me know via the same methods. But for now, thank you again for watching, and I hope to see you next time.